on a microscopic scale. So maybe at a macroscopic scale, it's difficult to envision time travel, but what about at a microscopic scale? What about at a quantum scale? Do we see or do we have time travel or not? You know, that could be a question too. In chapter 9, we saw that the laws of science are unchanged by combinations of the operations C, P, and T. This means that an antiparticle spinning in the anti-clockwise direction and moving from A to B can also be viewed as an ordinary particle. Spinning clockwise and moving backward in time from B to A. So this whole stuff about the sum over histories and the antiparticle doing one thing is basically the particle, the partner of the antiparticle, doing the spinning clockwise in the backward direction in time. So Feynman's way of, if you are not familiar, you might want to look up Feynman diagrams in particle physics or just Google some examples of them. You will see how he's very, all these like backward in time things are allowed in the Feynman diagrams. So similarly, an ordinary particle moving forward in time is equivalent to an antiparticle moving backward in time. So this whole stuff about time travel, maybe this is already something that's kind of happening in terms of the microscopic scales or the quantum scales or the particle scales, because we literally do have Feynman diagrams that are sort of used a lot in particle physics that do allow for this sort of like backwards and forwards interpretations of time depending on the particle that you're considering. If the particle is doing this one thing, its antiparticle could be doing the other thing in the backwards direction in time. As has been discussed in this chapter, in chapter 7, empty space is filled. So what we once considered empty space and just everything is empty and nothing much happening is actually a very busy space filled with these virtual particles. So there could be a lot that's happening in empty space that we are sort of unaware of, right? So as has been discussed, empty space is filled with pairs of virtual particles and antiparticles that appear together, move apart, and then come back together and annihilate each other. It's only empty because we're not measuring the particles and the antiparticles sort of separately. We are seeing this overall system having the annihilations between the particles and antiparticles, making space empty, but really there's a lot that's going on in that empty space. So one can regard the pair of particles as a single particle moving on a closed loop in space-time. So once again, one can regard the pair of particles, the two things together, the particle as well as the antiparticle pair, as a single particle moving on a closed loop in space-time. When the pair is moving forward in time from the event at which it appears to that at which it annihilates, it is called a particle. So from the event at which it appears to that at which it annihilates, it's called a particle. But when the particle is traveling back in time, from the event at which the pair annihilates to that at which it appears, so this is the particle at which it appears to where it annihilates, and this is where it annihilates to where it appears. So that's the closed loop of space-time. So in the first way, when the particle is traveling back in time, like I said, this way, from the event at which the pair annihilates to that at which it appears, it is said to be an antiparticle traveling forward in time. So once again, when the pair is moving forward in time from the event at which it appears to that at which it annihilates, it is called a particle. But when the particle is traveling back in time from the event at which the pair annihilates to that at which it appears, it is said to be an antiparticle traveling forward in time, or a particle traveling backward in time. The explanation of how black holes can emit particles and radiation was one member of a virtual particle-antiparticle pair. So remember how Stephen Hawking made the argument that black holes can sometimes actually emit things. This is how they have a temperature. So if they did not sometimes quantum fluctuations like emit particles, they would not indeed be having some sort of temperature. So Hawking radiation, if they don't have a temperature, there's not going to be a black body radiation. If they have a black body radiation, it means that they have a temperature.